Hello and welcome to my course in Transformation Semigroups and Applications. I'm Dr. A.T. Imam, a lecturer at the Department of Mathematics, Ahmadu Bello University, Zaria. This is the fourth lecture of the course, and in this lecture we are going to talk about orbits of a finite full transformation. So, given a full transformation alpha in Tn, an equivalence relation alpha tilde on the set Xn is defined by the rule two element x comma y in Xn are related if and only if x alpha s is equal to y alpha t. We defined this equivalence relation in our last lecture, lecture 3, and we explained that this relation is an equivalence relation on the set X. So it will partition the set into orbit. We even exemplify the concept of the orbit being the connected component of the graph associated with the map. So this orbit are precisely the connected component of the directed graph gamma alpha. In our previous lecture, we also explained how a graph can be associated with every map, where two points x and y having an edge between them if y is the image of x. So in what follows today, we are going to talk about the orbit of alpha, and we are going to show that this particular orbit that we just defined are of four kinds. So a map cannot have more than 4 types of orbit. It can have more than 4 orbits, but they are of 4 different kinds. So let us begin by lemma 2. So let's look at an orbit. An orbit, from the definition, is an equivalent class under this particular equivalence relation, which we define in this way. So if we assume omega is an orbit of alpha in Tn, and that omega is a subset of the image set of alpha, then there exists a positive integer r greater or equal to 1, such that for each x in the orbit can be written as x alpha square, x alpha r minus 1, where x alpha r is equal to x. So this orbit is forming a cycle. So this lemma is saying that whenever an orbit is contained in the image set, that is, if every point of the orbit is an image of alpha, then the entire orbit can be seen to form a cycle of some particular length r. So this is what we are going to show. So now, take an x in the orbit. Then since x is a member of the image, because in the assumption of the lemma, it is assumed that the orbit is contained in the image. So every point of the orbit is an image. That means we can choose another point of the orbit that map to x, such that x1 alpha is equal to x, because x is an image point. So therefore, the pre-image of x will also be related to x, and we can choose that a particular pre-image x1 that map to x, so that we have this. But then x1 also coming from the orbit, it means it's an element of the image. Then there will be a second point x2 that will map to x1. And if you continue in this way, you generate a sequence of points all coming from the orbit, x0 being the x, x1, x2 up to the infinity, because this sequence will continue indefinitely. For all and for each I greater or equal to 0, if you apply alpha I time on the point xi, you arrive at x, because x2 is the image of x1 and x1 is the image of x0. So if you start at any point xi here and keep on applying alpha I times, you eventually come back to the first element of the sequence. So, but this sequence being a sequence of terms from a finite set must contain repetitions, because our omega is finite, since the underlying set initially we are working in a finite full transformation. So we are dealing with a finite full transformation, so therefore everything is finite. So you have an infinite sequence whose terms are coming from a finite set. That means that sequence must contain repetitions. So if we assume xm is the first entry of the sequence to repeat, and xm plus r as its first repetition or reappearance, so there we assume that there is some point xm here that repeat for the first time, and that its first repetition occurs somewhere here at xm plus r. Then the claim is that m must be 0. So it has to be the first entry of the sequence that will start repeating eventually. So if you continue x0, x1, x2, x3 up to xm, and xm repeat somewhere at xm plus r, then you will eventually have to see that the first entry xm to repeat must be x0. So therefore, the first repetition in the sequence has to be xm, and it must repeat somewhere at xr. So we have to show that m is equal to 0. So for otherwise, if it is not 0, if m is not 0, then we will have xm plus r equal to xm. But then this will imply that if you apply alpha on both sides, you have xm plus r minus 1 equal to xm minus 1. And this is in contradiction to the choice of m, because we say xm is the first entry to repeat. And here we are seeing that xm minus 1 is also repeating as xm at xm plus r minus 1. So this is in contradiction with our initial choice of the image of the point of the index m. And so therefore m must be 0. So we have to assume that m is 0 over here. So the first entry in the sequence to repeat is xm, and its first repetition is at xr. So which means we have x alpha r equal to 0, meaning if you look at this relationship here, if x0 is the first entry to repeat, which is also equal to x, so it means x, and you apply alpha r times, you get back to xr, which is x. So x alpha r is equal to x. So this is the first observation we come up with. Therefore, it means the entirety of the set x alpha square, which is x alpha r minus 1, is contained in the orbit, where this is a cycle because x is mapped to this, and this point is mapped to the next, and so on, and the last point is coming back to the first entry by this equation, by this equality here. So therefore, we have the cycle contained in omega. If we can show that omega is also contained in this cycle, then we have achieved equality. So we have this inclusion as equation 1. Now, if you pick an arbitrary element y coming from omega, then as observed above, we can also arrive at y equal to y alpha s, but this is equal to y. So if you apply alpha s again one more time, you still arrive at y, so you still get y alpha 2s, y alpha 3s, and so on and so forth. And then by the definition of omega, since both x and the y are coming from omega, they are related, so they will have some non-negative integers u and v, such that y alpha u is equal to x alpha v. But then we can choose, since we are dealing with integers here, it is possible to choose some integer j with this property: j minus 1s is less than u, and u is less than or equal to j times s. But once we have this, then we can see that y equal to y alpha js from this particular series of equalities here, we arrive at, we can have this. So any multiple of s, if you raise alpha to any multiple of s and apply on y, you still get y. And this will now be equal to, so you break this by adding u and subtracting u. So you perform some little bit of indices here. You say plus u minus u, and then you have y alpha u, y alpha s, js minus u, which is equal to, because from here y alpha u is equal to x alpha v, and so therefore you have x alpha v, y to power alpha j minus 1, which is equal to, so you can now do the indices again, you can add the powers, and then you arrive at this. But then js minus u is a positive integer, and then you have v. So this is actually an integral power of alpha applied on x. So this will eventually be inside this set C. So this belongs to C. So therefore you have an arbitrary element y coming from omega, and it turns out to be an element of C. It means the entire omega is a subset of C. So you have the entire omega as being a subset of C here. So from equation 1 and 2 we can now have equality. So we see that omega is actually a cycle. So what we have shown here is that if you pick any element x from omega, then x alpha will still be in omega, and x alpha square is in omega, which is mapped to x alpha cube, and so on. And then this omega is forming a cycle. So you have a cycle in this way. So if an orbit is entirely contained in the image set, then that orbit will be a cycle of some length. So it means we have a definition now. So if r is greater or equal to 2 in our lemma, then the orbit is called a cyclic orbit. So this is what we call a cyclic orbit. And if it happens that r is equal to 1, then the orbit consists of only one single element and is called a singleton orbit or a trivial orbit of alpha. For this orbit, we can still have one more property of the orbit, that an orbit of alpha, for an orbit of alpha, if you restrict the application of alpha on the orbit, that is alpha restricted to the orbit, will be a bijection if and only if the orbit is a cyclic orbit. If you look at it from, if the orbit is cyclic, then from the lemma it looks like this. And so from the very definition of what we mean by cyclic orbit, we have this, where x alpha r is equal to x, and then it means we have a bijection, because if you just think of how alpha apply on this point, you can see that every point is mapped to one and only one, and every image appear only once actually, and so therefore this is a one-to-one and onto map here. So we have a bijection. So it's very clear that we have a bijection. And in the converse, if we assume that the orbit is not cyclic, then there exists some x not in the image, because the orbit is not cyclic. For cyclic orbit, every member of the point of the orbit must be an image. So we can have something not in the image, which means that point not in the image x is when you restrict on the map, the restriction of alpha on the omega, it will not be in the image of the restriction also. And so therefore the restriction of alpha on the omega would still not be an onto map. So you don't have a bijection. Okay. I think this is where we stop for this particular discussion. In the next lecture, we are going to look at orbits that are not necessarily contained in the image set of alpha. Thank you very much for your attention, and I hope to see you in the next lecture for a continuation of this discussion. Do not also forget to subscribe to our channel